Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the example of a particle on a string. Let's begin with a problem. A particle is hanging vertically on the end of a light, inextensible string of length 0.8 meters. It's set in motion with an initial horizontal speed u meters per second. So let's have a picture. There, that represents the information. There's the radius of the circle, the length of the string. Here's the mass, and here's the initial speed. Notice we've got the usual simplifications of a light inextensible string, so we don't need to consider either any change in length or any mass attributed to the string. Well, to deal with this, we need to draw ourselves the setup that we're going to get. We've got from the previous video, we've got the result that if you did it in a circular tube, smooth circular tube, then you would require a minimum speed satisfying u squared is greater than or equal to 4gr. That's where the r is the radius of the circle. So translating that into this problem, we've got r is 0.8, g is 9.8, so that means that the u squared value has got to exceed, or minimum value, of 31.36. To remind you, that really boils down to saying that the kinetic energy at the bottom has got to be equal to the potential energy gained by the time you reach the top. So you're saying what's u got to be for it to be just v equals 0 at the top, where v is the speed at the top. Now in this case it's a bit more complicated, as we shall see. Let's begin by thinking about how the forces work at the top of the circle. Well, in this case we've got the setup with the circle, and I've shown the mass with a gap so that I can show the forces, not getting confused with the forces that are on the string or anything else. So in this case we're going to have vertical forces, the tension and the mass times the acceleration, which is weight. Those two are going to act in concert at the top, and they'll produce the acceleration towards the center, which of course is expressed in terms of the speed that it's got at the top. So the v squared over 0.8 is the usual acceleration. So if we take resolving along the string as usual and applying F is ma, Newton's second law, we get T plus mg is equal to mv squared over 0.8. So if we're interested in the tension, as we shall see in a moment. The tension then is mv squared over 0.8 minus mg. Now, the fact that there's a minus sign in that right hand side there shows the interest in this problem, because it's very possible that mg will be bigger than mv squared over 0.8. In which case that would imply that the tension is negative. Well, that means that the string would be pushing the particle to keep it in circular motion, and that's not sustainable in this model. So we're interested then in what happens if we end up with a negative tension. Well, to put it in the terms of this question, we're going to insist that t has got to be positive, and that means we'll get a criterion on v. So there's what I've just said. Let's now insist that t is positive, so we end up saying that 0 is less than or equal to mv squared over 0.8 minus mg. So we can see in that inequation we can divide by the positive quantity m and multiply by 0.8, so we'll end up saying that v squared is greater than or equal to 0.8 times g. And we know that g is 9.8, so that will immediately give us a number. So at the top we need not just v is 0 or greater, now we need it to be bigger than this quantity 0.8g, and that makes all the difference. So let's look at the numbers. I got as far as v squared is greater than or equal to 0.8g, nothing else has changed, and I put g as 9.8 in, and we end up with the value 7.84. So in order to have a positive tension, or at least a non-negative tension at the top, V has now got to be bigger than the square root of 7.84, whereas with the circular tube it was just greater than or equal to 0. So where does that take us to then? Well, we need to work out what V squared is in terms of U, and that will come as before by energy. So at the bottom, half mu squared, that's the initial energy, taking the potential energy as 0, is equal to the energy at the top, that's a half mv squared, plus the gain in potential energy, which will be 2 times the 0.8, because that's the height gained, times mass times gravity. So that will simplify. We can divide by half m, which will mean that we've got an extra 2 on the right. So we'll end up saying that v squared is equal to, well, we'll end up with u squared is equal to v squared plus 4 times 0.8, which is 3.2 times g. So we can turn that into numbers using g as 9.8. So we'll end up with v squared plus, it turns out to be 31.36. Now that should look familiar. If you remember from the first slide, I said that that was the minimum value of u to get to the top. Well, that figures, doesn't it? Because on that basis we were saying that v was 0. But in this case we're going to say that v is bigger than that. It's the number we got on the previous slide. So that's the 7.84. So from that then we can proceed a bit further by saying that our minimum value of u squared is going to be equal to the minimum value of 7.84 plus that extra 31.36. So that gives us a number which is actually 39.2. You can see it's about that, even if not exactly, and that can be turned then by taking the square root into the answers to the question. It will be the square root of 39.2, which is 6.260. So etc. So that gives us the answer to the question as 6.26 meters per second, which is significantly bigger than it would have been for the answer in the case of a particle in a smooth circular tube. Well then, if we're insisting that the tension stays positive to the top, that's really the worst case. If we didn't give it enough speed to get to the top, there must be a critical point where the tension first goes 0. So let's look at an example which brings that into play. So here we have a light inextensible string as before, very similar setup, but this time instead of having the necessary 6.26, we've got 4.5. So I've shown the setup in the diagram. The radius is unchanged at 0.8. We've got the initial speed 4.5 when we're interested in the angle theta, which is the one at which the tension first goes to 0. Well, in order to do that we'll need a force diagram. So what will the forces in play be? There'll be a weight acting vertically at B, and there'll be, because the particle is going to be at B in that situation, and we'll have a tension acting along the radius, and we'll have an acceleration towards the centre, much as we've seen before. So there's the picture for that. I've given it a speed v at B, and we've got the weight and the tension and the acceleration towards the centre. So that we can turn into an equation of motion. As usual, it will be F equals ma, so we'll have T plus along the radius. mg needs to be resolved. Now there'll be a cos theta because the angle theta, which I've circled in this left hand diagram, will reappear as the angle between the weight and the tension. So that's the force that's effective, and that must be producing the acceleration. So we have mv squared over 0.8. Now with that we can simplify it considerably clearly, because we're interested in getting the tension. So the tension, because that's what's got to be 0. So T is equal to mv squared over 0.8 minus mg cos theta. So if we now put some numbers in, we'll have an m, and the first term will be 1.25 v squared, because 1 over 0.8 is 1.25, and we'll have minus 9.8 for the g times m times cos theta. So that's the expression which we've got for the tension. So there we are. I haven't put the m outside a bracket there, but otherwise that's just the same. Now in order to use that to find out where t is 0, we've got to relate v, which we don't know, to the u that we started with, and that will come in through the cos theta. So if we use the energy equation as usual, we'll have a half times m times 4.5 squared, that's the initial energy, and that will be equal to the energy at B, again assuming that the potential energy is 0 at A. So we'll have the kinetic energy, a half mv squared. Remember, the idea is to find out what v squared is from this equation, plus the change in potential energy from A to B. That will come in two parts. There'll be a 0.8 straight up, and then there'll be a 0.8 cos theta to get from O to the level of B. So that will be plus mg times 0.8 times 1 plus cos theta. And we know in this equation that g is 9.8. I'll need that in a moment, but it's probably simpler before we put the g in to get rid of the half m's. So we'll end up with 4.5 squared is equal to v squared, and then if we're dividing by m and multiplying by 2, we'll have 1.6 times 9.8 times 1 plus cos theta. So the 1.6 times 9.8 gives us 15.68. So if we make v squared the subject here, we get v squared equals, and it will be the 4.5 squared, which is 20.25, and then minus the 1.6 times 9.8, which is 15.68, times 1 plus cos theta. Well, we're getting there. So if we take the 20.25 and subtract from it the 15.68, we'll get 4.57, and that gives us then remaining the 15.68 cos theta, which has to be subtracted. Now that's beginning to look quite hopeful. We've got an expression for v squared there in terms of cos theta, and we can substitute that into the last typed equation, and that will give us an equation for t in terms of cos theta with a multiplying m. So let's do that then. There's the calculations so far. It's this equation that we want to quote on the next page and combine it with the last one, which is the 4.57 minus 15.68. So there's our two quoted equations on the left, and we want to get an expression for t. So t is 1.25 times m times v squared, which is 4.57, minus 15.68 cos theta, that's an 8, that's the first term, minus a 9.8 m cos theta. Now the numbers are getting quite complicated here, so we need to keep a clear head. The first, that we're going to get a combination of two terms. At the first one, the 1.25 times the 4.57 is going to be quite simple. Let's take an m outside the bracket, that makes it simpler. 1.2 times 4.57 is 5.7125. And then we've got a 1.25 times a 15.68, and that's subtracted, and there's an additional 9.8. So that gives us 19.6 for the first combination times cos theta, and we've also got the minus 9.8 cos theta that's left over on the second line. So finally, if we put that all together, we get m times 5.7125, and those numbers combine to give us 29.4 cos theta. Now you can begin to see what's going to happen here. If we're interested in the tension being 0, it will be that bracket that's got to be 0. So there's the calculation so far, and what we need out of this is to say that we can now tell that cos theta, where theta is the tension is 0, will be whatever's needed to make that bracket 0, and it will be 5.7125 over 29.4. That's roughly a fifth, 6 over 30. So that's roughly a fifth. That's the angle, so we can see that's making sense. And if we put that into the v squared expression, that will tell us that v squared is equal to 4.57 times 5.7125 over 29.4. Well, that's easy enough to do, isn't it? We can get an answer and then take its square root. So here goes. 4.57, that's exactly what I had on the previous slide. And we put that under a square root and work it out, and we get 1.23. So that tells us that the speed at that point where it comes out of the circle is equal to 1.23 meters per second. Well, okay, that's strictly the answer to the question, but we may anticipate now that if we've got a speed of 1.23, at that point it's going to come out of the circle and have the usual parabolic motion, and well, the string will go slack again there, tight again there, wouldn't it? So something dramatic would happen. But before it reaches that point, it would come out of the circle in the form of the usual parabola for a projectile. But for the present, the answer to the question is the speed is 1.23 meters per second. Well, that brings us to the end of this particular example. The next one is very similar. We've moved from a particle in a smooth circular tube to a particle at the end of a light inextensible string, and next we move to the particle on the outside of a cylindrical surface, and you may care to anticipate what differences there'll be in the calculations.